First day of final projects lab today. It'll be interesting to see what people are doing. And what I've been doing the last few days is trying to, after watching people fiddle around with interfaces between CPU and SRAM for doing video, I decided to implement that. And I implemented it using the Pancake CPU, the stack machine. And guys, if you want to talk, bail out. Okay? Thanks. And so what I did was to write a set of hardware and software that writes to SRAM from software and then uses SRAM as a video display. And the software detects the sync signals so that the CPU does not try to write while the SRAM is needed by the VGA controller. And so the hardware is actually relatively simple. The tiny CPU just has a clock, reset low, and then N2 is not VGA horizontal sync concatenated with not VGA vertical sync. So it is a 2-bit input which allows the CPU to detect both horizontal and vertical sync independently. Then out.0 is going to be mapped to VGA address, but we need to mess with it a little bit first, so I'm just going to do kind of embarrassingly trivial mapping. Out 1 is going to become the VGA data, but it needs to be manipulated too before being put into the VGA. And then out 2 is going to be, so this is VGA address, this is VGA data, and out 2 is going to be a combination of two signals. One is write enable, and the other signal is the low bit of the address. The reason for that is that the SRAM consists of 2 to the 18 16-bit words, and we want to address it as 2 to the 19th bytes. So we're going to use the address low bit here as a control to choose whether we want the upper byte or the lower byte of the SRAM. I map the color into 7 down to 5 red, 4 down to 2 for green, and 1 down to 0 for blue. But if you just do a straight mapping of 3 bits, 3 bits, and 2 bits into the high order bits of the VGA controller channels, DACs, you don't get very good dynamic range. you get kind of pastel-y kind of washed out colors. So before this signal goes into the VGA controller, it is range expanded through a lookup table. So what we're going to do is to map out one into we're going to define a color map whose outputs are red, green, blue, 10 bits each, and whose input is an index. And the index we're going to use is going to be out 1. The contents of the color map are really simple. It's really just a ROM. So module color map is given by an input 7 down to 0 of index, and then output register 9 down to 0 of R, G, and B. And the reason for the 9 down to 0 is that maps directly to the DAC bits on the VGA controller. And then we write always at star. We're going to write a combinatorial case statement. I'm not going to write this all out because it's very redundant. But the first case is going to be index of 7 down to 5. And then we simply enumerate 1 down to 7. And for each of these indices, we get to choose the value that we want for the red channel of the VGA. And I made the the 0 value always equal to exactly make it hex 0 here. Made it always equal to black, to no drive at all. And I made the 7 in this case be R equals 10 tick hex 3F F, which is full amplitude. But the intermediate values you can map however you like. And so I mapped them for perceptual equal weight so that I got a nice looking gray scale. And what worked pretty well was to use 4F, 8F, they're a little dark but not too bad, AF, FF, 1FF, and 2FF. 1, 2, 3, 4, 5, 6. Yeah. So those were the values that filled in here. And that gave a pretty good looking scale. These two might have been a little dark. So that might have to be squeezed up a little bit. But you can choose them however you like. You can choose to have only bright saturated colors, or you can choose to have all pastels, or any scheme you like. And there's a case statement There's an in case there, and there's a case statement for green and a case statement for blue that allow you to map the red and the green and blue independently and any way you want. This gives much more brilliant colors, better dynamic range. So there's a color map which connects the index to the red, green, blue channels, but then of course back in the main we have to assign M memory VGA red equal to R, MVGA green equal to G, and assign MVGA blue equal to blue, and these are the same signals you've been using all semester, so those are the direct input to the VGA control module. But an index has to be handled a little bit carefully, because index is going to be read back from memory. It's going to be read back from static RAM, and whether or not you use the high byte or the low byte depends upon whether you are writing an address, a VGA address, with an odd or even X value, whether the low order bit is set. So reading back from the VGA controller, coordinate X0 is the low order bit of the display, of the X display address, and if coordinate X is set, then we need to read SRAM DQ 15 down to 8. Otherwise, we need to read SRAM DQ 7 down to 0. So that decodes the low order bit of the address. The rest of the interface then is all done combinatorially. So SRAM address is 18 bits, and it has to come from 3 different possible sources. It has to be set to 0 when you press reset. Sorry. Erase what I just said. It has to be set to coordinate X, coordinate Y when you press reset. The data bus is set to 0. The static RAM is set to VGA controller output, and then when you press reset you get a black screen. When write is enabled, the CPU has to control the address, and when write is not enabled, the VGA controller has to control the address. And so we need, so we can write this as reset, and reset high in this case is normal operation because reset is active low. So reset high means we're not resetting. And then in that case we have to ask, is out to bit 0 equal to 1? If it is, we are not writing. So if this is 1, it means we're not writing, and therefore the output question mark, the output to the SRAM address should be coordinate y 8 down to 0, and we have to have 9 bits of y to get 480 resolution, followed by coordinate x 9 down to 1. We need 10 bits here to get 640 resolution. We only have 9 bits here, but the 10th bit is here. If we are writing, then the control output is out 0 from the CPU. And if we are resetting, then once again we are going to have the address bus be coordinate y 8 down to 0, coordinate x 9 down to 1. And while we're resetting, we're not going to bother to detect the low order bit. And why would that be? Well, I haven't written it yet, but the reason is that the data bus is going to be set to all zeros, and so you write both bytes at once. So we're going to assign SRAM chip enable CE not to 1 tick binary 0, which is to say we're going to turn on the chip. We're going to set SRAM output enable not to 1 tick binary 0. We're going to enable the output. We're just going to leave it enabled. SRAM DQ has to detect whether we're in reset and whether we're writing or reading. And if we're in reset, we're not in reset. If reset is high, then we have to detect whether we're writing or reading. If we are reading, then we float the bus. Because if we're reading, the CPU is driving the bus. Or the SRAM is driving the bus. If we're writing, then out 1 from the CPU is driving the bus. And if we are in reset, we're just going to 0 the bus. That ensures that we write black when we press reset. And that really should be 16 tick binary 0. So now lower byte enable not needs to be driven according to both reset and whether we're reading or writing. If we're in reset mode, we don't want to step through all the addresses. We're stepping through every other X, so we have to write the upper byte and the lower byte. So both SRAM upper byte not and SRAM lower byte might not have to be 0 if we are resetting. So reset question mark, reset question mark. If we are reading back from memory in normal operation, we have to read both the upper and the lower byte because the index is going to be selected from either the upper byte or the lower byte. So again, both of them have to be 0 if we're doing a normal read. But if we're doing a write, we have to discriminate based on output to bit 1. So out to bit 0, are we writing or reading? If we are reading, then if we're reading, then we're going to set this to 0. We're going to set this to 0. If we are writing, we are going to set it to out to bit 1, which is going to be the low order bit of X. So output to bit 1 is going to carry the low order bit of X. Otherwise, it is not out to bit 1. And otherwise, if we're in reset mode, we want 0. And finally, write enable SRAM write enable is if it's in reset. If we're in reset mode, we want 0 because we just want to write all of memory with black. Otherwise, we want to have out to bit 0, out to bit 0 control the reset. So that's all the hardware we need. So these all multiplex the control lines depending on whether we're in reset mode or whether we're reading or writing from the CPU. And since the CPU, which I've already erased, since the CPU gets the VGA sync signals as input, we can make sure that we only change these signals at appropriate times so that we don't make the display flicker or draw random dots. All right, so the other half of this then is the software. Given that we're using tiny CPU, using the pancake CPU, you need to use a compiler to, which I haven't really named yet, but I'm thinking about just calling it syrup, to generate the appropriate code to generate these addresses in some strange format with packed so that the upper 9 bits are Y, the lower 9 bits are X, that the 0 bit of the X ends up in bit 1 of output 2, and map the colors in some way and detect sync. Any questions on the hardware? It's nice and regular. It's very regular. Everything has the same control structure: reset, output, multiplexers. The color map makes a much nicer set of colors than just brute force using the bits that come off the 8-bit index. All right. So there's a bunch of ports that are defined, a bunch of constants. VGA. So this is in the constant section of the program. We're going to define VGA address as 0, VGA data as port 1, VGA control as port 2, white as 255, and black as 0. And in X, the maximum number of X is about, I used was 630, and NY was 479. And there are some variables declared: temp, temp 2, count, count X, and count Y. But a lot of the work is done by an inline function, which is going to draw a point. And it's kind of homely. So we're going to have an inline for speed. It's going to be inline VGA point. And this is going to take on the stack the color, the Y coordinate, and then the X coordinate, where this is top of stack. So Y coordinate is second on the stack, color is third on the stack. First thing we're going to do is parse out the low order bit of the X coordinate and save it in a special location. So we're going to, first of all, dupe the X coordinate, duplicate the X coordinate on the stack, then do a bit AND with 1, that isolates the low order bit, and then store that into temp 2. Secondly, we're going to do a 1 shift right of the X coordinate, which is now high on the stack, and store that into temp. Then we're going to, now we've popped X off the stack, so Y is now top of stack. So we're going to do a 9 shift left to put the Y coordinate in the high address, which is what's required by the hardware. Then recall temp and do a bit OR, and then output it to VGA address. Output to VGA address. At this point now, we've used X and Y off the stack, so the next thing on the stack is the color. And we have to process that a little bit. If temp 2, in other words, if the low order bit of X is set, then shift left, and if, since color is on top of stack, it's in a position after we do the check for temp 2 to just shift it left if necessary, and then output this to VGA data. Finally, we recall temp 2 again, shift it 1 left, so it's in the bit 1 position, and output VGA control. Since we did the shift left, it guarantees that the low order bit is a 0, which enables the write. So bit 1 now carries the value of the low order bit of X, and bit 0 is guaranteed to be 0, which forces a write. Then the only thing we have to do is 1 second later is do output a 3 to VGA control, which guarantees that the write enable is pulled high again. Write enable is pulled high, which stops the write, and that's the end of the inline for writing a point. Yeah.
Why is there a second shift right?
Where? This one? Okay, because we need X coordinate 9 down to 1 as the low order bits of the address. So we have to shift off the 0 bit.
If temp 2 get a shift left.
Uh-huh.
Okay, if it's not temp 2, then it will still output to VGA data.
Yeah, so the color was still on the stack, and we just haven't shifted it so that it's in the low order position where you need it for the even X addresses. We need it shifted to the left for the odd X addresses. How many ways are there to mix up the odd and even addresses? I found all of them. So in the main, then, the program section, main has a relatively simple structure. We just, since the stupid processor doesn't initialize its ports on reset, you need to output a 3 to VGA control, which makes sure that write enable is high and no writing is going on. And I implemented a timer also, but I'm not going to include that in this. Then we just set count Y to 0. And then while count Y and Y less than, while count Y is less than the number of Y that we're choosing to draw, which is about the whole screen, we set count X to 0 while count x is less than nx, do. And at this point, we need to detect the sync, which is coming in on port 1. So we need to do an if in from the sync port, and if you'll remember, the sync port has an input of not VGA horizontal sync, or not, concatenated with not VGA vertical sync. So if we're in horizontal sync and vertical sync are active low, so if either of these is active, then this concatenation will be non-zero. So if this is non-zero, it means that we're safe to write because the VGA is not using SRAM, so we can use it. Then count x, 1, shift right. This is the color. I'm indexing the color by the x position, so I'm drawing stripes. I'm shifting it right 1 because I wanted the stripes to be 2 pixels wide. So that's the color. Then we put in the y position. Then the x position, and then call VGA point. Add 1 to the count, and end if. End while. Add 1 to count y. End while. After that, I dumped the program into an endless loop to halt it, but this has the main interaction with the video. It only writes when the sync is valid for writing. It blasts out a point, increments the various counters, and then goes through the loop again, waiting until the sync is valid. If we detect the sync, so then the question is, how fast is it? If we detect the sync, it writes the whole screen in a little over 2 seconds. So it writes the 307,000 VGA points in about 2.5 seconds. If we don't detect sync, if we just hose the stuff out there with and let the artifacts fall where they may, it takes about 250 milliseconds to write it all. So this is using the slow version of the CPU. So if you're using the fast version of the CPU, it would be about twice as fast. So it would be about 125 milliseconds to write all of memory with no sync detection. It turns out that the memory on these boards, I thought it was 20 nanosecond SRAM. It's actually 10 nanosecond SRAM. And so you can toggle it very, very fast. You can toggle it at 100 megahertz. And the CPU in this case is running at 100 megahertz. Yeah.
Count y, 1 add.
Mm-hmm.
Should it be inside the index?
Very good. Very good. I was just going to bring up that there's a bug here, but you caught it. What'll happen? It could skip it.
Yeah, we'll skip it.
That's right. It could well skip. It turns out that I made a mistake when I wrote this initially, but I left it in for just to see if anybody would pick it up. And that is that this increment happens inside the sink and is therefore atomic with the write to the screen. But this one is outside the sink, and therefore on certain boundary conditions, we might find that we don't go into the sink, but we still increment the y, and therefore skip a line. I haven't seen that happen, and I'm not sure why. But it should be inside the sink, you're quite right. So, using the pancake processor to manipulate SRAM, this is pretty efficient. It's pretty fast. It's not as, I mean, one would always like to go faster. Using M4K blocks, it's a good deal faster. But M4K blocks on the DE2 don't have enough bits to get color. If you go to the DE2 115, there's enough M9K blocks to get full color to the VGA. And then you don't have to manipulate SRAM. You just use dual-ported M9K blocks and write whenever you want, read whenever you want. Good questions. Luke. I can't find any information one way or the other, which implies to me that they haven't thought it through yet. Which is another reason to use the pancake processor, because it does work. I spent all morning fiddling with the lookup table. It's really addictive. You know what I mean? Oh, I want it a little greener and a little redder, but not quite so blue. So you can have good fun with that. I like logarithmic intensity distributions, but it's a little hard to tell because most monitors, it turns out, are not linear in intensity with the color that you choose. They have a gamma, which is set on various monitors to some value between its value to the second to someplace between 2 and 3.5. So you have to take the value, the intensity is proportional to the number you put in on the DAC channel raised to some power that's more or less unknown and variable between monitors. So you have to tune this for the monitor you're using, and I don't know how general it is. I don't know how stable those values are anymore. With CRTs, they used to be quite variable. With LCDs, I don't know. Anything else? Let's head to the lab. Pardon me? Ah, yes, that's important. After this week, we're going to go directly to the lab. There will be no more lectures, which is important for video note. And so, yes, Monday we will meet in the lab at 11 o'clock.